Hello everyone, I am Kirti Amolik, Assistant Professor in RBNB College, Sri Rampur. In the last lecture of the M.Sc. one of this M.Sc. second year Organic Chemistry course, that is CHO 352, second section Asymmetric Synthesis, we have studied the examples of the chiral pool strategy. In that example, we have studied the chiral auxiliary. What are chiral auxiliary? Their examples, how they are incorporated in the substrate to direct the enantioselective synthesis. Now we are going to consider the next point in the asymmetric synthesis is how to consider the yield or how we can measure the yield of the reaction product in the asymmetric synthesis. We know that in the general reaction, we always determine or calculate the efficiency, or we can measure the efficiency of the reaction products in terms of the practical yield or yield of the product, and it is calculated as the percentage yield. So for any reaction, we can gives the formation of the product in terms of the percentage yield, but in the enantioselective reaction we cannot give it by percentage yield, because one enantiomer is found to be major product and very small quantity or very trace amount of the in other enantiomer may be formed, or in some cases 1%, 2% undesired enantiomer may be found, or remaining 98% or 99% will be the major enantiomer is formed. So in order to calculate the exact yield, it can be measured in terms of the enantiomeric excess. So this term is very important in order to calculate, or in order to study the yield obtained, how much amount of the enantiomer is present or obtained in the given asymmetric reaction. Now it is called as the enantiomeric excess. That means the excess of the one enantiomer present over other. It is called as the enantiomeric excess. So when we consider any reaction, if the reaction has the enantiomeric excess of the 98%. That means 98 is enantiomeric excess. That means 2% is the racemic mixture obtained in the reaction. That is 1% will be the one enantiomer. So that will form the racemic mixture with the another enantiomer, and we will get the 2% of the racemic mixture, which is undesirable. So 98 will be the enantiomeric excess. Now let us consider the example in order to study the concept of the enantiomeric excess. Now see this reaction. In this reaction, first compound is the acid chloride compound, and we know that it is chiral compound. It may be present in the optically pure form. Now first we are going to incorporate the chiral auxiliary in the substrate molecule, so that we will get the highest amount of the enantiomer. So let us react this acid chloride with the reactive chiral auxiliary, So in the last lecture we have studied two chiral auxiliary. First is the oxazolidinone molecule. It is also called as Evans chiral auxiliary, or it is also called as valine derived chiral auxiliary. So this chiral auxiliary, oxazolidinone molecule, this is now react with the acid chloride in simple SN2 type of substitution reaction. So nucleophilic attack plus takes place at the carbonyl group. O- is formed, and O- on reversible chlorine as a good living group will get removed. So it is simply a simple SN2 type of the displacement reaction. Then the nitrogen which is present, nitrogen having the positive charge, hydrogen will get removed in order to satisfy the valence. So we are getting this compound. Now this compound is present in the high enantiomeric pure form, because now chiral auxiliary it is attached to the substrate, so it becomes chiral. Now the substrate becomes the chiral, and now if we want to react with the particular reagent, this is now chiral molecule, and after incorporation of the chiral auxiliary, so again we can remove the chiral auxiliary and convert it into stable compound by reacting with the LiOBn. So this is lithium salt of the benzyl alcohol. So this benzyl alcohol, it is reacted BNO minus, and this is lithium plus. So the BNO minus, it is reacted here with this carbonyl group. Reversal of the charge takes place and nitrogen, this will get removed. So we can write here this bond undergo cleavage. So we are getting this type of ester molecules are formed. Now this is the chiral compound, highly pure single enantiomer, okay, or this another enantiomer may be present, but it is present in very smaller trace amount. So this is chiral enantiomerically pure compound, it is reacted with the LiOBn, and we are getting now the mixture of the enantiomer, or we can say we are getting the single enantiomer, but very small quantity of another enantiomer may be present, very small quantity. So it is, we are getting 98:2 mixture of the enantiomer. That means 98% of one enantiomer is present and 2% of the another enantiomer is present. So this is percent ratio of the mixture of the enantiomer. So for this we can calculate the enantiomeric excess, such as, now here 98% one enantiomer is present and 2% other enantiomer is present. So now this 2% of the undesired enantiomer, it will forms the racemic mixture with the 2% of another enantiomer from this 98. So 98 minus 2, it will give the 96. So 4% racemic mixture is generated and 96% of the single enantiomer is present in the pure form. So it is called as the 96% of the enantiomeric excess for this reaction. So enantiomeric excess gives the amount of the single enantiomer, that is one enantiomer, how much quantity is excess of the another enantiomer. Now different types of the methods can be given for the separation of the enantiomer. We know that racemic modification involves the different types of the method. So one of the method used traditionally, it is the chiral chromatography. So in chiral chromatography, what happens, the chiral stationary phase is used, so that it will separate the two enantiomer. So it will get bind to one enantiomer, other enantiomer will be get separated. So chiral chromatography is used, and in some cases salt or some derivative compounds are synthesized, so that the salts have forming the different diastereomer. So enantiomer will get converted into diastereomer, and we know that the diastereomers having the different physical and chemical properties. So in such a way that we can separate the enantiomeric excess. Now let us consider another example here. If we consider the two alcohol are present, generally in presence, when we consider the compound having the free NH2 group, amine group is there, or free alcoholic group is there, in that case we can attach any electrophilic salt, or we can attach the chiral auxiliary to that molecule, or the chiral stationary phase may be used. So this free group reacted with the electrophilic chiral auxiliary or reactive salt, and it will get converted into diastereomer so that they can be easily separated. So one of the example is if we consider the alcohol, secondary alcohols are given. This is general example. If we consider the secondary alcohol here, any alcohol may be taken. So we have written here R groups. So these are the enantiomer of the secondary alcohol. Mixture of the enantiomer is present. Now if we reacted with this mixture, the Mosler's acyl chloride is reacted. So if we react this with the Mosler acyl chloride, this is the one of the salt. It containing chiral center. It is present in the enantiomerically pure form. Now this salt reacted with each enantiomer differently so as to give the diastereomer. So if we react this with the OH group that having alpha orientation in alcohol, so in that case we are getting the compound A and this is compound B. So A compound is generated when this alcohol reacted with this acyl chloride. Because this OH group is alpha oriented, it is below the plane. This OH group having the lone pair of electron act as the nucleophile and it will displaces the chlorine here. So this chlorine is get removed and ester is formed. Now this ester, it contains the alpha oriented isopropyl group because alpha oriented OH group is present. So we are getting the A diastereomer. Now this alcohol in which the beta oriented OH group is present, it is reacted with the acid chloride, same salt, Mosler's acyl salt. So that we are getting the beta oriented OH group containing OR containing the ester compound. So this will be the B diastereomer. So we are getting the diastereomeric mixture of the salt. So we can easily separate these diastereomers now because this having the different physical and chemical property. We can separate them by resolution method or we can separate them by chiral chromatographic separation. So we can, in this way we can separate the mixture of the enantiomer in the suitable by the using suitable salt like Mosler acyl chloride salt or the compound. Now in this case we have used this chiral auxiliary. We can use also the different chiral auxiliary. Now how this oxazolidinone molecule we have seen here, but it is synthesized from the valine amino acid. Now let us see the reaction for the formation of the chiral auxiliary oxazolidinone. So the synthesis of the oxazolidinone molecule involves first we have used the valine, S-valine enantiomerically pure, one of the amino acid. This amino acid further on number of the steps, it will get converted into cyclic enantiomerically pure chiral auxiliary. So in that first step is the reduction of the carbonyl group. Either we can convert it into ester, can use this ester derivative, or we can also use the corresponding acid derivative. So this ester or acid compound, it can be reacted with the borane compound. So dimethyl sulfide borane compound is used, or borane derivatives is used for the reduction. We know that in borane compound, hydrogen and borane will get added on the same side of the carbonyl group or the double bond. So here reduction takes place, hydrogen will get added on the carbonyl group. Hydrogen will get added on the carbonyl group and borane will get added on the oxygen, and further reduction takes place. So you are getting the corresponding CH2OH. So two steps, in the two steps, two hydrogen atoms are added to the carbonyl group and we are getting the corresponding alcohol. Now after this reduction, it is allowed to reacted with the compound or electrophilic compound diethyl carbonate molecule. Now this compound now contains two nucleophiles, NH2 and OH group. So in the first step, nucleophilic attack of the nitrogen takes place. Then this proton is removed in order to satisfy the valency of the nitrogen, or in this case it may be removed by the solvent. So here this O minus, but this compound contain the two good living group OAT, these are the good living group. So reversal of the charge may take place, that will remove the one of the OAT group and convert this into the stable compound. So we are getting the amide ester compound is obtained here, ester, and this is the amide linkage. Now another nucleophile is present in the same molecule. Again reversal of the charge takes place, cyclization occurs, and we are getting the corresponding cyclic molecule is obtained here. CH2. Now this OH group attacks from the above side to this carbonyl group. So this group will be on the below side. So this CH2, CH3, CH3, this on reaction cyclization, it will get converted into corresponding compound, and this is your required chiral auxiliary, that is the chiral oxazolidinone molecule. So in this way we can synthesize the first chiral auxiliary, it is oxazolidinone molecule. Now the second example for the reaction involving the asymmetric synthesis, we consider this. In this case again acid chloride is reacted, already we have reacted, this type of reaction we have seen. Acid chloride if reacted with the, now this is another chiral auxiliary, it is norepinephrine derived chiral auxiliary. Norepinephrine derived chiral auxiliary, it is attached to the acid chloride compound, and this chloride compound, it on removal of the chlorine we are getting this type of the substrate. That is, now this is present in the enantiomerically pure form. Now here the carbonyl group is present, ketone or amide linkage is there, and this is chiral molecule, enantiomerically pure. These protons are found to be acidic because they are adjacent to the carbonyl group. So if we remove this acidic proton, we can carry out the alkylation type of reaction. So if we use the bulkier strong base, we can form the enolate, and this enolate on alkylation gives the corresponding reaction or alkylation in highly asymmetric way. Now let us see, we can use here the corresponding trimethyl disilazide compound, bis trimethyl disilazide compound. This act as the base, this compound act as the strong base. So it is the base similar to LDA, lithium diisopropyl amide. So this amide bases, lithium and the nitrogen containing bases, these are bulkier and very strong bases. So this type of the base, it will abstract this proton present on the alpha carbon atom, so thereby generating the negative charge. It is stabilized over this carbonyl group. So this negative charge or carbanion, we can similarly write this structure as, it is stable, stabilized partially over this carbonyl group. This is the enolate or enol is formed, and this enolate immediately in second step, it is reacted with the corresponding allyl iodide compound. So this is the structure of allyl iodide compound. So this enolate is nucleophilic at alpha carbon atom. Iodine will get removed. So we are getting the corresponding structure in which allyl group is added on the alpha carbon atom. So this allyl group is found to be added from the back side of this alpha carbon atom, because front side or the above side is found to be sterically hindered. This double bond, it having this structure, this nitrogen containing ring is present, which is bulkier, we know that, and it will shields the one face of the double bond. So one face will get protected or shield. So electrophile cannot approach from the both faces. Now these groups are present above the plane, beta oriented. So front face of the double bond is shielded, so that the electrophile must attack from the bottom face or below face. So this front face is sterically hindered. We can write this as, this is the front face, and from the below side attack takes place. From this below side reacted with the corresponding electrophile allyl iodide. So attack takes place from this below side, because above side is the, or front side, it is the sterically hindered due to presence of the groups on the chiral auxiliary. So we are getting only single enantiomer. So this is the reason why we are getting the enantiomerically pure compound, only single enantiomer is obtained. So this is the product obtained in the alkylation reaction. Now further, if we reacted this with the lithium aluminum hydride, which is the strong reducing agent, so in this case what happens, this nitrogen, this carbonyl will get, this will get removed, and this carbonyl will get reduced by the transfer of the two hydrogens on the carbon atom. So you are getting the OH group. Here OH, carbonyl group will get converted into OH group. So we are getting OH, and in second step it is allowed to reacted with the tertiary butyl dimethylsilyl chloride compound. It is also called as the TBDMS. It is the tertiary butyl dimethyl silyl chloride. This is the structure. This is the bulkier protecting silyl protecting group. Bulkier silyl protecting group used for the protection of the alcohol, or generally primary or secondary alcohol. So this is the primary alcohol. OH group is formed in the first step and immediately it will get protected with the dimethylsilyl chloride. So we are getting the structure and we are getting the high yield of the enantiomeric excess, that is we are getting more than 99% of the enantiomeric excess is obtained in this reaction. So highly enantioselective reaction can be carried out by using the chiral auxiliary. Now let us consider the next example, alkylation of the chiral enolates. Alkylation of the chiral enolates. We know that the enolates are generated by treatment with the acid or base. If any organic compound that containing the acidic proton, for example ketonic groups are there, or active methylene containing compounds are there. For example, when two carbonyl groups are bridged or present, so this CH2 group, it is called as the active methylene group. This protons becomes more acidic because these two carbonyl groups are adjacent to this carbon atom. These having minus I minus R effect, strong withdrawing groups are present. So when molecules containing the strong electron withdrawing groups, that will withdraws the electron density in the carbon in the organic compound, and so the adjacent hydrogens become the electron deficient or acidic in nature. Again, if you consider the acetylene molecule, it also contains the acidic protons. Nearly pK value is 25 for this type of compound. It contains the acidic hydrogens. Also this type of the beta diketone compound or beta diketone, or it may be ketone or it may be ester compound, any carbonyl group, except the acid and other acid derivative. So only the ester and the carbonyl compound, that is ketonic compound, and ester compound can shows this type of the property. It may contain the acidic or active methylene group. So this proton can be easily removed by the base. Carbanion is generated and it is very well stabilized over this both carbonyl group by resonance, stabilization as well as hyperconjugation. So in this case, this carbanion is found to be stable and it may react with the alkyl halide, like any alkyl halide or any electrophile to give the alkylation reaction. So any R group can be added on this reactive carbon atom or the carbon containing acidic proton. So this is called as the alkylation reaction. So enolates are generated with the acidic compound. Now the acidic compound are those that containing the highly strong electron withdrawing group. So strongest electron withdrawing group is the nitro group, then comes the aldehyde ketones, and then comes the cyanide, ester, amides, etc. So nitro group containing compounds are very acidic in nature, having the acidic proton. So in that case also we can generate the carbanion, and in the ketonic compound we can also generate the carbanion. So similar example we are going to study here. Here acid chloride is given. If we reacted with the Evans chiral auxiliary here, we are getting the corresponding enantiomerically pure compound is obtained. This is only single enantiomer. Now this carbonyl compound containing these alpha hydrogen atoms, these are present adjacent to the carbonyl group, so they are acidic in nature. Now these acidic protons, these are removed by the base like LDA. LDA is the lithium isopropyl amide, diamide, lithium diisopropyl amide. This is the structure of the LDA. LDA is the bulkier but very strong base. So it will it is kinetically, it shows the kinetically controlled reaction. It forms easily the enolate ion in the 100% enolate ion, so as it is the strong base. So these protons are removed and enolate is generated. Sorry, here negative charge is present on the nitrogen atom. So this negative charge removes this proton and this lithium will get bonded to the oxygen atom. So we will get so this is lithium enolate is generated. We are getting the lithium enolate. Now this lithium enolate, next step, it is allowed to reacted with the electrophilic compound like benzyl bromide compound. We know that benzyl halides are highly SN1 as well as SN2 reactive electrophiles. Alpha halocarbonyl compounds are also the reactive electrophiles, so they can used in the alkylation reaction. Now here double bond is present, negative charge is there on oxygen, so this carbon is found to be nucleophilic in nature, this alpha carbon atom here. But in this case we can see here the back side or the below side of the substrate, it is sterically hindered. It is not easily accessible for the electrophile. This is electrophile and this is nucleophile. So this is going to react with this carbon atom, but the below side is sterically hindered. So attack of the electrophile or the approach is takes place from the above side, because this it is sterically hindered side. It is shielded sterically, so it is protected by the isopropyl group. So electrophile will approach from the above side or front face of this double bond. This is front face and this is bottom face. Bottom face is shielded here or protected by the presence of this bulkier group. So SN2 type of this displacement reaction takes place and we are getting the corresponding product in very high enantiomeric excess, and we are getting this beta oriented alkylation or beta oriented group is added on the double bond. So there is beta oriented benzyl group is added adjacent to the carbonyl. So reaction is highly enantioselective. So this is the alkylation of the chiral enolate. So generally we know that the enolates are not chiral, but the attachment of the chiral auxiliary and further the generation of the enolate by strong base like LDA, it becomes the chiral enolate. And this chiral enolate, it is accessible, or the double bond is accessible from the one side, that is front face only. So we are getting the single enantiomer. This single enantiomer is obtained. So this becomes highly enantioselective reaction. So this alkylation reaction can be also carried out in the enantioselective manner or asymmetric manner. So that's all for today. Now in the next lecture we will start some reactions of the asymmetric synthesis like asymmetric hydrogenation, asymmetric hydroxylation, etc. And we will also study which type of the chiral catalyst and reagents are used in the asymmetric synthesis. Thank you.